Hello, everyone. My name is Gitipat Abhishatarison or Patrick from Nokia Bell Labs. Oh, sorry.
Okay. No. Yeah, welcome Dr. Gitipat Abhishatarison for the presentation PointPresence, an online habitat for multi-user mixed reality telepresence. Dr. Gitipat finished his PhD at the University of California, Riverside and a postdoc training at CMU. He is currently a networks researcher at Nokia Bell Labs in New Jersey, working on mixed reality and network system. Let's join me welcoming Dr. Gitipat for his presentation.
Thank you. I almost introduced myself. Thank you so much.
Awesome, thanks.
All right. So today I'm presenting this PointPresence online habitat for mixed reality, multi-user mixed reality telepresence. In our group has Eugene Shai, Limin Wong, Hansek Chang, and Sarit Mukherjee. So we start with this idea of application compute network symbiosis, right? So we have this MR application, right, that can do different things for the user, right? And some MR application require networks, right? It usually require a lot of network bandwidth to transfer point cloud, mesh to the end user. And some work already look at how to reduce the network bandwidth requirement by applying segmentation, segment the scene and stream only some objects, or apply some point cloud compression, right, when streaming MR. And some work about like scaling compute, right? Those cloud scaling solution that not look at the application, right? Like application agnostic solution, like cloud scaling. When we are introducing this technique, right, or a solution called camera selection that can reduce the compute and network requirements for MR telepresence. And at the same time, we introduce this reactive algorithm that create kind of like compute loop, right, that interact with segmentation compression and then the compute resources of the MRH. And we combine this and call it PointPresence. So let's come back to the context a little bit, right? So we are talking about MR telepresence that enable this immersive experience, right? You have this 3D physical space, right, with people in the scene and some background objects, and we place this 3D cameras to capture the physical space. And we capture the actual physical space. We are not using avatar or the head model or anything like that. And so that the user can move freely in the space, right? And then they interact with each other across the network and create this kind of like the MR telepresence. And a typical configuration would be like 360 capture, right, of the physical space. It can be 8 cameras capturing this space. And this is kind of like example of that, right? So we have this, left user using this 8 camera to capture the space, and this camera stream, sent to MRH for processing, and then the process model sent to the user on the right-hand side to the rendering device of that user. And the same thing happened to the right user, stream this camera to the MRH and send to the rendering device of the left user. And what is the problem, right? The key problems of this kind of application or this kind of scenario is that it requires high compute, right, for processing multiple camera at the same time, right? We can see 8 for one scene and it can multiply to more than that, right? So, and all the camera stream have to be processed in a similar latency, right? Otherwise, we are creating some distortion of the process MR 3D model. And, like I said, it can, increase to, more than 8 cameras, depending on how many scenes the MRS is supporting right now. So, and we do this experiment to show that, more than, if the edge support more than like 5 cameras, it cannot, maintain the latency for 30 frames per second anymore, right? And the higher latency, when it's processing more camera and also higher variance, right? This could be an indicator of like a poorer user experience. The second problem is unpredictable compute demand. So the compute demand of Telepresence depend on context and user posts, right? So, for example, you can see that this the remote user can look at different direction to this person, right? And this field view can change at any time, so it's difficult to predict. And the subset of camera that point to the user field view should have like highest point resolution, right? And this change over time with the user context as well. This also show that the point resolution for the same object with different distance to the camera and different camera resolution also change, also vary. Right, so we need like a highly flexible pipeline that respond to this GPU and CPU demands, right? We're talking about like millisecond time scale, right? So those like cloud scaling approach work in like a second cloud scale second time scale wouldn't work in our scenario. The third challenge is high GPU contention. So if it, like I mentioned, that if we stream 3D model directly, it would consume significant bandwidth, right? Like 3 to 5 gigabit per second. So we need some semantic understanding of the 3D model, right? We can use this ML-based model to segment the object of interest, right? And only transmit those objects to the remote user. And if we have again multiple camera that need to use this ML-based model on the same GPU, right? We're creating a lot of contention on the GPU, right? You can see here that if the number of camera go to like 16 camera, the GPU processing 16 camera concurrently, the ML-based latency would increase to 65% of the end-to-end latency. So this is the third challenge for this Telepresence. So we propose PointPresence, right, with the design principle of simplicity and efficiency, right? So PointPresence is deployed on the MR edge, as I mentioned, processing multiple camera at the same time. It can be deployed at RIC or RAN RIC or enterprise server close to the user. Simplicity means that we have to design the pricing to achieve like 33 milliseconds per frame, right? So that we can achieve at least 30 frames per second. Efficiency meaning that any decision that our controller make, it has to make multiple impacts on the output. And the key feature of the PointPresence are intelligence camera selection and reactive pipeline design. At a high level, PointPresence reduces bandwidth and compute requirements, or MR, by first camera selection. So basically, it selects the camera that's most relevant to the user field view, and the outcome is that it reduces network bandwidth and compute workload on the MR edge, because it processes only a subset of camera instead of all of them. And second, PointPresence uses scene segmentation. So basically segment the entire scene and filter only those relevant objects and send to the user. So it basically reduces the network bandwidth required for Telepresence. The last one is point cloud compression, because raw point cloud can be huge. We need algorithm to compress the point cloud using this OCT3 or KD3, convert it to bitstream, and then send it over the network. It can reduce network bandwidth requirement 10 to 20 times. All right, so let's understand more about this camera selection, right? So we have the user A and user B again, right? And then user B look at the right-hand side of user A. So the camera that capture the right-hand side of user A are activated, right? At the same time, user A look at the left-hand side of the user B. So the left-hand cameras of user B are activated, right? The rest of the camera can be deactivated at that time, right? So we, with these ideas, we can reduce the number of camera by selecting only the camera that relevant to the user field view. And at each time, the MRH process around 2-3 cameras instead of 8 camera streams all the time. And the reactive pipeline design, right? So let's look at the typical, the normal pipeline first, right? So we have the 3D world. We have this model camera to capture the world. We have the scene segmentation to filter the objects. We have this point cloud compression to reduce the data size of the point cloud. And this happened on the, we call encoder MRH, right? And then send this compressed point cloud to the to another user. And this decoding user do decompression of the point cloud and merge the point cloud from multiple camera into a single model and then render it onto the device, right? And because the scene segmentation mostly work on GPU, right? It's a CPU workload, and the point cloud compression is a CPU workload, right? So if we have this process to monitor the processing latency of scene segmentation, we can adjust ML frequency, right? Meaning that how many frame per second that we feed into GPU to do this scene segmentation, right? To reduce the workload, we reduce the frequency of the ML tasks, right? And the same thing can happen on CPU as well, right? So if you can monitor processing latency of the point cloud compression, we can adjust point resolution, right? Reduce or increase number of points to compress. Then we can, maintain an acceptable latency for these tasks. Right? Okay, and then we, combine everything and do this end-to-end implementation of PointPresence. We have an encoder for each camera, right? And then we have the scene manager to control, the encoder of the cameras, and stream over the network. And then at the decoder, we have this component to combine the model from multiple cameras, and then send to the renderer to render the scene. For experimental setup, so we implement our system on MRH compute with server-grade specs, right? 4 A100 GPUs and 128 CPU core and 512 memory. So we compare this PointPresence and baseline. So basically, PointPresence do everything, right? Camera selection, reactive pipeline, scene segmentation, point cloud compression. The baseline doesn't have camera selection and reactive pipeline. It just process all the frames from all the camera all the time. And the data set we use is the open data set with 3D person in a 3D room, and we place 8 virtual cameras to form a 360-degree capture. And the user field view continuously move around the person, right, to force the camera selection to be continuously executed, creating a challenging scenario for our pipeline. right? So we measure two metrics of interest, end-to-end latency, the time from when the camera captured the frame until the 3D model emerged and then ready to be sent to the renderer. And we also have SSIM, which represent the visual quality perceived by the user. So we do experiment with more than 10 scenarios with different network bandwidth, different network delay, compute instance size, meaning the different number of CPU cores and different size of the GPU by using the MIG to scale up and down the GPU resources with object walking in the scene or not walking in the scene and different capture camera resolutions. We find that on average, PointPresence can reduce end-to-end latency around 1.5 times, and for 80% of the time, PointPresence stream 47% less point because we select camera and only send points from selected camera to the end user, and we achieve a similar SSAM to the baseline. So PointPresence also saves significant power of the MRH. We have the MRH process two concurrent scenes, meaning that 16 cameras on the same MRH. And we measure a different metric, but basically the power consumption for both CPU and GPU reduced significantly because of the PointPresence camera selection and reactive pipeline design. And also we test a scenario where the user pose change significantly, right? So basically we have these three objects in the scene, right? 0, 1, 2, right? And the virtual user start with field view 0 by looking at object 0, right? And go from start to end, and at the end it come back to the starting point again and change the field view to the next object, object 1, and then do again for the next round, looking at object 2 with field view 2, right? So this create like abrupt user poses, right? Like change both the position of the virtual user and also the direction, right? And we show that, with these red lines that represent this significant change, the FPS and point resolution and the point cloud distance doesn't be impacted by this abrupt pose changes, meaning that our proposal is it's robust to abrupt user pose changes. So yeah, this is our project, and you can see more detail in the paper. Yeah, thank you so much.
Thank you, Patrick. Do you have any question? Okay, so I have a question. Your work achieved 3.5 times end-to-end latency reduction. So could you tell me what were the biggest contribution to this improvement during the computation?
The main thing is the pricing latency, right? Without this PointPresence, like pricing every time, the latency, introduced by the processing of this frame, right? Both CPU and GPU, because this has to be processed, after one another, right? It has to process, run the GPU task first and then CPU, right? When the latency increase, it increase both, this end-to-end latency together, right? So this task cannot be executed in parallel. So that's why the computation latency is high. And also in some scenario, we find that if the, because PointPresence reduce the bandwidth requirement, right? if the application data streaming exceed the network bandwidth capacity, then there's a lot of like retransmission, right? Like the packet loss, and then it has to retransmit the packet until it can recover everything, and then the application start to decompress, right? Using this compression technique, it can decompress at that point. So it has to wait for all the packet to arrive before it can decompress and then go with the pipeline. So these are the two factors that we find in the pricing and network latency of this Telepresence.
Okay. Yeah. Thank you so much.
Thank you.
Yep. Thank you, Patrick, for the great presentation.